Hello, Professor. Our team has two members, Niancheng Xu and Nubu Hamok. Our project theme is about the classification of celestial objects. Our data comes from the Kaggle website. This is a very important and interesting survey, which is almost conducted once a year recently. The Sloan Digital Sky Survey has been one of the most successful surveys in the history of astronomy. It started from year 2000. The Sloan Digital Sky Survey has created the most detailed three-dimensional maps of the universe ever made, with deep multicolor images of one-third of the sky and spectra for more than 3 million astronomical objects. The target variable of our project is class, which would help us to recognize different categories of stars, like galaxy, star, or quasar, depending upon several related variables, so that this dataset will allow us to learn and explore all phases and surfaces, past, present, and future of the SDSS. We will be classifying the class object based on 17 or less variables to predict whether the celestial object is a star or galaxy or a quasar. We have interest in space science, and thus we decided on doing an analysis on this data to get insights about astronomy and cosmology. First, let's have a general view of the concept of the three types of object. A galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter, and the star is an astronomical object consisting of luminous spheroid of plasma held together by its own gravity. And at last, a quasar is an extremely luminous active galactic nucleus, in which a supermassive black hole with mass ranging from millions to billions of times the mass of the Sun is surrounded by a gaseous accretion disk. Then let's see the information of the dataset. From the result, we can tell that there are total 100,000 samples and 18 columns. By the way, there are no missing values here. It's not a small sample size, so the accuracy of the prediction can be better. However, when I first saw the name of all these independent variables, I found it very difficult to understand the meaning of them. So next, I will simply introduce the meaning of these variables. There are so many variables here, so I just picked two important ones. First, the Ra is the angular distance measured eastward along the celestial equator from the Sun at the March equinox to the hour circle of the point above the Earth. Second, redshift is a phenomenon where electromagnetic radiation from an object undergoes an increase in wavelength. By the way, U, G, R, I, Z are responses of the 5 bands of the telescope. The variables colored in orange are those who don't have a real meaning in the determination of the object. They are just some IDs or numbers. So we chose to drop these variables. Then the results of the prediction will be more reliable. From this plot, we can see that galaxy is the most popular system in our universe, while at the same time, quasar is the most uncommon system in the universe. We also did some box plots to see the distribution of these variables. Here, we just choose two as the example. The plot shows that the Ra is evenly distributed, and the mean of Ra is about 180. The right one's variable is U, which is a type of magnitude fit of the object. This variable has some outliers, but we can't remove them now because we still don't know if these values are really outliers or just the values of quasar, which has the smallest sample size. From the map, we easily find that G, R, I, Z have a high correlation between each pair. If we don't deal with them, there may be a multi-correlation problem later. So we'd better reduce the number of dimensions into one. Luckily, there's no problem with other variables. Then here we visualize the plot of GRIZ to prove the correlation problem again. In each picture, the dots are all gathered in a closed area, and they are not normally distributed. So we did the PCA to reduce the number of these 4 variables. In the result, those 4 variables are replaced by a new variable, PCA value. So at last, we only have 5 independent variables left, which makes our work much less now. Otherwise, there will be over 1 million numbers to deal with. Then we start to use different methods of supervised learning to do the prediction of classes. First, we use logistic regression. The result shows that the general accuracy of logistic regression is about 94%. And from the curve, we can see that when the parameter C reaches about 900, the performance is the best. So I chose 900 to do the report. The accuracy improves to 97% now. Only for the quasar, the accuracy is a little bit low, which is also already 94%. This is a very nice result, but we still have to try some other methods. Decision tree's accuracy is very high. It's already 99% for the test set. From the plot, we find that when the sample split is 10 and the sample leaf is 10, the performance is the best. So we chose 10 as the value of parameters. The result shows that under this situation, the accuracy is still as high as 99%. So till now, decision tree is a perfect method for prediction. The next one is KNN. The accuracy is very low compared to previous 2 methods. The reason for this result may be that the classes all distributed in a closed area, which leads to the high misclassification. For the largest sample size, Galaxy, it also has a low accuracy, so we must give up this method. LDA's accuracy is low, only 76%, so we didn't go deeper now. And naive Bayes' accuracy is almost as high as decision tree, but it's still not better than decision tree. And SVM has a normal performance. Then we go to the last method, random forest. Random forest is amazing. From the left plot, we can see that when the number of estimator reached 300, the accuracy reaches the peak. So we choose 300 as the parameter. Then the accuracy reaches 99%, which is even a bit higher than that of decision tree. And for the largest sample size, Galaxy, its accuracy even reaches 100%. This is really surprising. And after all, we can find that decision tree and random forest have the best performance to predict the class of the celestial object. At last, we try to see the importance of all these features and find that the redshift is the most important feature. I think this is why the accuracy of decision tree and random forest can reach that high. So finally, we got some conclusions. First, random forest is the best supervised learning method to predict the class of celestial object. Second, Galaxy is the most common celestial object in the universe. Third, the redshift is the most important feature to decide which class the object belongs to. And the last one, ZGRI, 4 different types of magnitude fit have a strong relationship to each other. According to these findings, we try to give some suggestions on the future prediction of the celestial object. First, try random forest and decision tree first to conduct the prediction, so the accuracy will be high and the cost can also be low. And second, focus on the redshift of the object, which is the most important feature, so that we can have a general view. That's all. Thank you very much.